Welcome to Sleeping Researcher, your peaceful companion for gentle science narration designed to help you relax and drift into a restful sleep. Here we explore fascinating scientific ideas with calm, soothing words that ease your mind while expanding your curiosity. Today, we embark on a quiet journey into the mysterious world of quantum mechanics. This is a realm where the rules we know from everyday life no longer apply, and where particles can exist in multiple states at once, instantly affect one another across distances, and behave in ways that seem almost magical. These strange, counterintuitive phenomena challenge our deepest understanding of reality itself. As we gently explore these concepts, you may find your thoughts drifting, your breathing slowing, and your mind opening to the wonder of the very small and very strange. Quantum mechanics invites us to see the universe through a different lens, one that is both beautiful and baffling, yet full of profound insights into how nature truly works. If you enjoy this calm exploration of science and want to continue your journey with more soothing narratives, please like this video and subscribe to Sleeping Researcher. Together, we will uncover the quiet mysteries of science, helping you relax and learn one peaceful story at a time. Now, let us begin our tranquil voyage into the curious and captivating world of quantum mechanics. Imagine a world so small that the very fabric of reality seems to shimmer and flicker in ways that defy our everyday intuition. This is the realm of quantum mechanics, a branch of physics that emerged in the early 20th century and forever altered how we understand the universe. At scales smaller than atoms, the classical laws that govern planets and billiard balls no longer apply. Instead, particles behave like waves, existing in multiple states at once, and outcomes are described only in terms of probabilities. It is a world where certainty gives way to uncertainty, and the act of observation itself can influence what is observed. This strange and fascinating domain has not only challenged the foundations of physics, but also opened doors to new technologies and philosophical inquiries about the nature of reality. Quantum mechanics originated from a series of puzzling experiments that classical physics could not explain. For instance, the behavior of light as both a wave and a particle, or the discrete energy levels of electrons inside atoms, hinted at an underlying reality far more complex than previously imagined. Scientists such as Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger contributed to a new framework that described these anomalies through abstract mathematical formulations. This framework replaced the deterministic predictions of Newtonian mechanics with a probabilistic language, where the exact position or momentum of a particle could never be simultaneously known with absolute precision. This principle of uncertainty became a cornerstone of quantum theory, revealing a universe that is fundamentally unpredictable at its smallest scales. One of the most intriguing aspects of quantum mechanics is the phenomenon of superposition, where particles can exist in multiple states simultaneously until measured. This concept challenges our classical understanding of objects having definite properties at all times. Alongside this comes entanglement, a mysterious connection between particles that allows their states to be instantly correlated, regardless of the distance separating them. Such phenomena suggest a deeply interconnected and non-local universe, where information and influence transcend conventional limits. These ideas not only stretch the imagination, but also underpin revolutionary technologies like quantum computing and quantum cryptography, which promise to transform information processing and security. As we explore these strange behaviors, we begin to glimpse a reality that is richer and more complex than once thought. The revolutionary nature of quantum mechanics extends beyond science into philosophy and our very notions of reality. The idea that observation affects outcome raises profound questions about the role of consciousness and the nature of measurement itself. Debates continue about whether the wave function, the mathematical object describing quantum states, represents physical reality or merely our knowledge of it. These discussions remind us that quantum mechanics is not just a set of equations, but a gateway to deeper understanding about existence and the limits of human perception. As we delve further into this captivating field, we encounter a landscape where certainty is replaced with wonder, and the familiar world reveals its hidden layers. For centuries, classical physics provided a reliable framework to understand the natural world. From the majestic motions of planets to the gentle flow of rivers, the laws formulated by Newton and Maxwell elegantly described phenomena at scales familiar to human experience. Objects followed predictable paths, forces acted in measurable ways, and the universe appeared to operate like a vast, intricate clockwork. However, as scientific inquiry ventured into the realm of the very small, the atomic and subatomic scales, this comforting picture began to unravel. The principles that once seemed absolute no longer sufficed to explain the behaviors observed in experiments. Particles appeared to defy the neat determinism of classical mechanics, challenging the very assumptions that had grounded physics for centuries. It was in these tiny domains that the classical worldview showed its limitations, revealing the need for a radically new approach to understanding nature's fundamental workings. At the heart of this shift lies the realization that particles such as electrons do not behave as tiny billiard balls moving along fixed trajectories. Instead, they exhibit wave-like properties, spreading out and interfering in ways that classical physics could not predict. The famous double-slit experiment beautifully illustrates this counterintuitive behavior. When electrons pass through two narrow slits, they create an interference pattern characteristic of waves. Yet when observed, they seem to behave like discrete particles. This duality, particles acting both as waves and as particles, defies the classical categories and invites us to reconsider the nature of reality itself. Such phenomena highlight the inadequacy of classical concepts like position and velocity when applied to the quantum realm, where uncertainty reigns supreme and precise knowledge of certain pairs of properties becomes impossible. Another striking departure from classical intuition is the concept of superposition. In the quantum world, particles can exist in multiple states simultaneously, only settling into a definite state upon measurement. This principle challenges our everyday experience, where objects have well-defined properties at all times. For example, an electron can be thought of as existing in several places at once, or having various energies until an observation forces it into a singular outcome. This profound idea necessitated a new mathematical framework, quantum theory, to describe probabilities rather than certainties. It is this probabilistic nature that sets quantum mechanics apart, replacing the deterministic laws of classical physics with a landscape governed by likelihoods and potentialities. Furthermore, quantum mechanics introduces phenomena like entanglement, where particles become linked in such a way that the state of one instantly influences the state of another, regardless of the distance separating them. This spooky action at a distance, as Einstein famously described it, contradicts the classical notion that objects only affect each other through local interactions. Entanglement reveals a deep interconnectedness embedded in the fabric of reality, suggesting that at the quantum level, the universe behaves in ways that challenge our conventional ideas about space and time. These insights underscore why classical physics, with its localized, deterministic perspective, falls short when describing the quantum domain. As we reflect on these extraordinary features, the wave-particle duality, superposition, uncertainty, and entanglement, it becomes clear that quantum mechanics provides a profoundly different lens through which to view the natural world. Classical physics, while remarkably successful within its domain, cannot capture the richness and subtlety of phenomena at the smallest scales. This realization invites us to embrace a new paradigm, one that blends mathematical rigor with philosophical depth, opening doors to questions that challenge our understanding of reality itself. With this foundation in mind, we now prepare to explore the fundamental principles and intriguing experiments that have shaped quantum theory into the remarkable science it is today. At the heart of quantum mechanics lies one of its most striking and enigmatic revelations, the concept of wave-particle duality. This idea asserts that entities we once considered purely particulate, such as electrons, photons, and other fundamental particles, can also exhibit behavior characteristic of waves. In our everyday experience, waves and particles are distinct. Waves ripple and spread through space, capable of interference and diffraction, while particles are more localized, discrete objects following definite paths. Yet at the quantum scale, these distinctions blur. Through carefully designed experiments, scientists observed that electrons, when passed through narrow slits, produce interference patterns, a hallmark of wave behavior, rather than the impact patterns expected of tiny solid balls. This duality challenges the classical intuition that had dominated physics for centuries, reminding us that the microscopic world obeys rules profoundly different from those we observe in daily life. The wave-particle duality does not imply that electrons or photons change their nature arbitrarily. Rather, their behavior depends crucially on how they are observed and measured, a subtlety that lies at the core of quantum theory. To appreciate wave-particle duality more deeply, it helps to consider the famous double-slit experiment. When particles such as electrons are fired one by one through two closely spaced slits onto a detecting screen, an interference pattern emerges over time, bright and dark bands, reminiscent of water waves overlapping and combining. This pattern is surprising because each electron seems to pass through both slits simultaneously, interfering with itself in a way no classical particle could. Yet, if a measurement device is placed to determine which slit the electron passes through, the interference pattern disappears, replaced by a distribution characteristic of particles traveling through one slit or the other. This experiment reveals a profound truth. The act of measurement fundamentally alters the behavior of quantum objects. The wave-like nature becomes apparent only when we refrain from forcing the particle to reveal its location prematurely, illustrating the delicate interplay between observation and reality in the quantum domain. This interplay fuels much of the philosophical wonder and scientific investigation surrounding quantum mechanics. The mathematical framework that captures wave-particle duality introduces the concept of the wave function, a complex probability amplitude that encodes all possible states of a quantum system. Unlike classical particles with precise positions and velocities, quantum entities are described by wave functions that spread out over space, embodying a range of potential outcomes. When a measurement is performed, this wave function collapses to a specific state, manifesting the particle-like attributes observed experimentally. This mathematical abstraction, though difficult to visualize, provides an incredibly accurate description of quantum phenomena and underpins technologies such as electron microscopy and quantum computing. The wave function's dual character reflects the nuanced reality that particles are not simply points moving through space, but rather entities whose existence and properties intertwine with probabilities and wave-like behaviors. Embracing this duality expands our conception of matter and energy, inviting us to rethink the fundamental building blocks of nature. Wave-particle duality also extends beyond electrons and photons, encompassing many particles traditionally viewed as discrete objects. Neutrons, atoms, and even molecules have demonstrated wave-like interference under carefully controlled experimental conditions. These observations reinforce the universality of quantum principles and suggest that the wave-like nature of matter is not confined to the smallest scales, but a fundamental aspect of the quantum world. As the scale of mass and complexity increases, the wave characteristics become increasingly subtle and difficult to detect, yet never fully vanish. This realization bridges the quantum with the classical, hinting at a continuum rather than a strict divide between waves and particles. It also poses intriguing questions about the nature of reality and the limits of human perception. Exploring these questions continues to inspire physicists and philosophers alike as they delve deeper into the mysteries of the quantum realm. As we contemplate the wave-particle duality, we begin to appreciate how quantum mechanics invites us into a world where our classical intuitions are gently set aside. Particles that spread like waves, probabilities that solidify into reality upon observation, and the subtle dance between measurement and existence. All these phenomena weave together to form the tapestry of the quantum universe. The journey through these ideas leads naturally to other fascinating quantum features, such as superposition and entanglement, which further challenge our understanding of separateness and locality. With the foundation of wave-particle duality firmly established, we now turn our attention to these equally remarkable phenomena, continuing our exploration of the quantum landscape. To delve deeper into the mysteries of quantum mechanics, we consider one of its most iconic demonstrations, the double-slit experiment. This simple yet profound setup involves firing particles, such as electrons or photons, toward a barrier with two narrow slits. Behind this barrier lies a detection screen, where the particle's arrival is recorded. Classical intuition might suggest that each particle passes through one slit or the other, creating two distinct clusters on the screen. However, what emerges instead is a pattern of alternating bright and dark bands, known as an interference pattern. This pattern is characteristic of waves interacting, peaks reinforcing and troughs cancelling each other. But here, it appears even when particles ascend one by one, as if each particle interferes with itself. This phenomenon gently challenges the very notion of particles as discrete, localized entities, inviting us to see them also as waves spread across space in a state of probability. The double-slit experiment thus becomes a visual gateway into the quantum realm, where particles and waves are not separate categories, but intertwined aspects of reality. What makes the double-slit experiment especially puzzling is the role of observation or measurement. When detectors are placed at the slits to determine through which slit a particle passes, the interference pattern disappears, replaced by two distinct bands corresponding to classical particle behavior. It is as if the act of measuring collapses the wave-like nature into a definite path, altering the outcome fundamentally. This interplay between measurement and the system itself hints at the elusive boundary where quantum possibilities crystallize into classical facts. It also raises profound questions about the nature of reality. Does the particle have a definite position before measurement? Or does the act of observation bring that position into being? The experiment invites us to embrace a world where certainty is replaced by probabilities, and where the observer plays a subtle yet indispensable role. This aspect of quantum mechanics, so counterintuitive and delicate, continues to inspire both philosophical reflection and scientific inquiry. Another striking facet of the double-slit experiment is the concept of superposition, which emerges naturally from the observed interference. In quantum terms, a particle passing through the double slits does not choose one path or the other in any classical sense. Instead, it exists in a superposition of both paths simultaneously, its wave function spreading across the two slits and combining on the far side. The interference pattern results from the constructive and destructive interference of these overlapping probability waves. This phenomenon beautifully illustrates how quantum entities defy our everyday experiences, where objects occupy definite locations. Instead, the quantum world is a landscape of possibilities, where particles embody multiple potential states, until an observation collapses the superposition into a singular outcome. The double-slit experiment stands as a testament to the elegance and enigma of quantum superposition, marking a profound departure from classical physics. Extending from the insights of the double-slit experiment, we begin to appreciate the profound implications for our understanding of locality and causality. The experiment hints at the non-local character of quantum mechanics, where the behavior of a particle is influenced by the presence of both slits, even when it seems to be traveling through just one. This subtle connectedness, invisible to classical intuition, lays the groundwork for further quantum phenomena such as entanglement, where particles become linked over vast distances. The double-slit experiment thus not only reveals the dual nature of matter and light, but also gently nudges us toward a deeper comprehension of the interconnected fabric of the quantum world. As we prepare to explore these fascinating concepts, the double-slit experiment remains a luminous beacon guiding us through the intricate dance of particles and waves. Building upon the delicate balance revealed by the double-slit experiment, we encounter the remarkable concept of quantum superposition. At its heart, superposition tells us that quantum particles, such as electrons or photons, do not simply travel through one path or another. Rather, they exist in a blend of possibilities simultaneously. Imagine a particle not as a tiny billiard ball confined to a single location, but as a whispered symphony of multiple states coexisting in harmony. This notion defies the binary certainty we experience in our everyday world. Instead of being here or there, the particle embraces a spectrum of potentialities until a measurement is made. This strange coexistence is not merely theoretical. It is fundamental to the behavior of quantum systems and underpins much of the technology that is beginning to emerge from quantum science. To visualize superposition, we might picture an electron as a delicate wave spread across space, carrying within it a probability pattern rather than a fixed position. Until we observe this electron, it does not choose a single location, but remains in a state of many possibilities, all entwined and overlapping. This is the essence of superposition. Particles exist in multiple states at once, a phenomenon that eludes classical explanation and challenges our deepest intuitions. It is as if the universe holds its breath, suspending reality in a cloud of alternatives, only collapsing into a definite state when interaction forces nature's hand. This interplay between potential and actuality is at the core of quantum weirdness and compels us to rethink the very notion of reality itself. The implications of superposition extend far beyond philosophical curiosity. They manifest in practical phenomena such as quantum interference, where overlapping states combine to produce patterns that would be impossible if particles behaved like classical objects. Moreover, superposition is the foundation for quantum computing, where qubits harness this multiplicity of states to perform computations in parallel, promising exponential increases in processing power. These advancements rest on the astonishing fact that a quantum bit can be both 0 and 1 simultaneously, a direct consequence of superposition. Yet, the mystery of superposition also raises profound questions about observation and reality. The act of measurement, so central to collapsing the superposition into a single outcome, remains a topic of debate and exploration. Various interpretations of quantum mechanics attempt to explain this transition, from the idea of wave function collapse to the possibility of many parallel worlds unfolding side by side. Each perspective offers a different way to understand how a particle that exists in multiple states can suddenly appear to choose one. This ongoing dialogue between theory and experiment enriches our understanding and deepens the enigma at the heart of quantum physics. As we continue to unravel the layers of quantum mechanics, superposition stands out as a luminous illustration of the quantum realm's departure from classical expectations. It invites us to embrace a world where uncertainty and possibility are intertwined, and where the act of knowing shapes reality itself. From the gentle waves of probability to the intricate patterns of interference, superposition is a cornerstone of the quantum landscape, guiding us toward further marvels such as entanglement and quantum tunneling. With this foundation laid, we move forward to explore the curious phenomenon where particles become mysteriously connected, transcending space and time. Imagine a sealed box containing a curious feline companion, a vial of poison, and a tiny radioactive source. This setup, known as Schrödinger's cat, is a thought experiment devised to illustrate one of quantum mechanics' most perplexing ideas: superposition. Inside the box, the radioactive atom has a 50-50 chance of decaying within an hour, which would trigger the release of poison and lead to the cat's demise. Until we open the box and observe, the cat exists in a strange blend of states, simultaneously alive and dead. This unsettling coexistence challenges our everyday intuition, where things are either one way or another, never both at once. The cat's predicament is a metaphor for how quantum particles can inhabit multiple states at the same time, a principle at the heart of superposition. Unlike classical objects, quantum entities do not settle into definite conditions until measured. This thought experiment invites us to contemplate how the act of observation collapses this superposition into a single reality. bridging the gap between quantum uncertainty and the world we perceive. Superuniverse woven with probabilities rather than certainties. Quantum particles such as electrons or photons exist as clouds of potential outcomes described by a mathematical entity called the wave function. Until an observation is made, these wave functions encompass all possible states simultaneously. Schrödinger's cat serves as a vivid analogy, encapsulating how a system can be in multiple, seemingly contradictory states without contradiction at the quantum level. This idea defies classical logic, where something cannot be both true and false at the same time. Yet, in the quantum domain, the universe appears to embrace this ambiguity as a fundamental feature. The notion that reality is not fixed but fluid until measured invites profound philosophical reflections about the nature of existence and knowledge, nudging us to accept that our classical perspective is only a limited lens through which to view a far stranger reality. The implications of superposition ripple through modern physics and technology, inspiring innovations such as quantum computing, where bits called qubits can exist in multiple states simultaneously. This capability promises to revolutionize computation by harnessing the power of parallelism inherent in superposition. However, maintaining these delicate quantum states requires isolating qubits from their environment, preventing the natural tendency toward decoherence, the loss of superposition through interaction with the outside world. Schrödinger's cat thus also symbolizes the fragile boundary between the quantum and classical worlds, where the mysterious rules of the microscopic realm give way to the familiar solidity of our macroscopic experience. Understanding and controlling this boundary remains one of the great challenges in quantum science, driving ongoing research into the measurement problem and the transition from possibility to reality. Reflecting on Schrödinger's cat, we are reminded that the quantum world does not conform to the neat categories of life and death, presence and absence. Instead, it thrives on a subtle dance of probabilities and potentialities, inviting us to expand our intuition beyond everyday experience. This thought experiment encourages us to embrace uncertainty not as a limitation, but as a fundamental characteristic of nature itself. It provokes us to reconsider the role of the observer, suggesting that observation is not a passive act, but an active participant in shaping reality. As we ponder these ideas, we prepare to delve deeper into the quantum realm, exploring how particles become entangled, mysteriously linked across space and time, a phenomenon that pushes the boundaries of our understanding even further. When we consider the act of measurement in the quantum world, we encounter one of the most profound puzzles in modern physics, the quantum measurement problem. In classical physics, measuring an object seems straightforward. We simply observe a property without fundamentally altering it. But in quantum mechanics, the very act of measurement appears to play a much more active role, causing the system to choose a definite state from a cloud of many possibilities. This enigmatic transition from a superposition of states where a particle can exist in multiple configurations simultaneously, to a single definite outcome, is what physicists call the collapse of the wave function. It is as if the universe holds its breath, suspended in uncertainty, until an observation precipitates a moment of clarity. This collapse is not predicted by the deterministic equations governing quantum evolution, which instead describe a smooth, continuous change over time. Rather, it introduces a sudden, discontinuous jump, a process that defies our classical intuition and challenges the very nature of reality itself. The measurement problem invites us to ask, what exactly constitutes a measurement? Is it simply the interaction between a quantum system and a measuring device? Or does it require a conscious observer to bring about the collapse? Different interpretations of quantum mechanics offer varying answers to this question. The Copenhagen interpretation, for example, suggests that measurement causes the wave function to collapse, but leaves the mechanism somewhat mysterious and tied to the role of the observer. On the other hand, interpretations like the many worlds theory propose that all possible outcomes continue to exist in branching universes, and no collapse occurs at all. These perspectives remind us that our understanding of measurement is not just a technical matter, but touches upon deep philosophical questions about observation, reality, and knowledge. The challenge remains to reconcile these views with empirical evidence and to develop a coherent framework that captures the essence of quantum measurement without contradictions. Experiments have pushed the boundaries of what we know about measurement, revealing that the process is subtle and complex. Quantum systems can be gently probed, revealing partial information without fully collapsing the wave function, as seen in techniques like weak measurement. These approaches hint that the boundary between quantum superposition and classical definiteness is not abrupt, but may involve a gradual transition influenced by the environment and interactions with other systems. This idea is central to the theory of decoherence, which explains how entanglement with the surroundings effectively hides quantum superpositions, making them appear as classical outcomes. Yet, decoherence does not solve the measurement problem entirely. It explains how classicality emerges but leaves open why a specific outcome is realized in a single experiment. It is this lingering mystery that continues to inspire both theoretical and experimental efforts in the quest to understand the quantum measurement problem. As we deepen our exploration, we encounter the intricate interplay between the quantum system, the measuring apparatus, and the observer, all woven into a tapestry of probabilities and potentialities. The measurement problem is a reminder that the quantum world resists simplistic explanations and invites us to rethink the nature of reality and information. It challenges the classical notions of objectivity and determinism, suggesting instead a universe that is participatory and dynamic, where outcomes are not fixed until observed. This profound insight pushes us to consider new frameworks and novel experimental designs, seeking clues hidden in the quantum fabric. As we leave behind the measurement problem, our journey continues toward the fascinating phenomenon of entanglement, where particles become mysteriously linked across space and time. This strange connection defies classical logic and further challenges our understanding of locality and causality. The peculiar nature of entanglement not only deepens the puzzle of quantum measurement, but also opens doors to revolutionary technologies like quantum computing and secure communication. Let us now turn our attention to this remarkable aspect of the quantum world, where the boundaries between separate entities blur and the universe reveals yet another layer of its subtle, interconnected reality. Entanglement is one of the most captivating and mysterious features of quantum mechanics. It occurs when two or more particles become linked in such a way that the state of one particle instantaneously influences the state of the other, no matter how far apart they may be. This connection is not mediated by any known force or signal. Rather, it seems to transcend ordinary spatial separation, challenging our classical understanding of how the world operates. In classical physics, objects are assumed to be independent unless they interact through some local influence. However, entangled particles behave as parts of a single, inseparable system, with their properties entwined in a manner that cannot be explained by any conventional mechanism. This phenomenon was famously highlighted in the 1935 paper by Einstein, Podolsky, and Rosen, who argued that entanglement implied spooky action at a distance and questioned the completeness of quantum theory. Yet, countless experiments since then have confirmed that entanglement is real, and that the universe does not adhere strictly to the principles of locality that once seemed so fundamental. One of the most intriguing aspects of entanglement is that the measurement of one particle's property, such as its spin or polarization, instantly determines the corresponding property of its partner, even if they are separated by vast distances. This instantaneous knowledge defies the classical idea that information can only travel at or below the speed of light. It suggests a profound underlying unity where the universe behaves as a holistic entity rather than a collection of isolated parts. The entangled state is represented mathematically by a single wave function describing the entire system, rather than separate wave functions for each particle. When a measurement is made, the wave function collapses and the correlated outcomes become apparent. This collapse appears non-local, meaning it cannot be explained by signals traveling through spacetime, further unsettling our intuitive grasp of cause and effect. Entanglement thus forces us to reconsider the varying notions of separateness and independence that underpin much of classical thought. Beyond its philosophical implications, entanglement also offers practical possibilities that were once thought to belong only to the realm of science fiction. Quantum computers, for example, leverage entanglement to perform complex calculations far beyond the reach of classical machines, using the combined states of entangled qubits to explore multiple possibilities simultaneously. Similarly, quantum cryptography harnesses entanglement to create communication channels that are theoretically unbreakable, as any attempt to eavesdrop on the entangled particles would disturb their state and be immediately detected. These emerging technologies promise to revolutionize computing and secure communication, yet they also depend on mastering phenomena that seem to defy ordinary experience. The strange counterintuitive behavior of entangled particles thus moves from abstract curiosity to the foundation of a new technological era. As we continue to explore entanglement, it becomes clear that the classical concepts of space, time, and causality are not sufficient to fully describe the quantum world. Instead, entanglement reveals a reality where particles are connected in a way that transcends traditional boundaries, pointing toward a deeper, more intricate structure of the universe. This interconnectedness suggests that quantum mechanics may be hinting at a more unified framework, one that reconciles the apparent contradictions between quantum phenomena and the classical fabric of reality. The journey into this subtle domain challenges our intuition and invites us to expand our understanding of what it means for particles to be separate or connected. It is within this context that we begin to glimpse the profound implications of entanglement, setting the stage for further exploration of quantum phenomena that continue to reshape our view of the cosmos. In the mid-20th century, physicist John Bell introduced a theorem that would profoundly deepen our understanding of entanglement and the nature of reality itself. Bell's theorem provided a concrete way to test whether the strange connections predicted by quantum mechanics could be explained by any local hidden variables, that is, underlying factors confined to each particle's immediate surroundings. The theorem established inequalities, now known as Bell inequalities, which set limits on the correlations that any local, realistic theory could produce. If these inequalities were violated, it would imply that no local theory could fully describe the behavior of entangled particles. This insight was revolutionary because it put to the test the very idea that particles could only influence one another through signals traveling at or below the speed of light, a principle deeply rooted in classical physics. Bell's work thus paved the way for a series of experiments designed to explore the fundamental principles underpinning quantum mechanics. These experiments aimed not only to observe entanglement, but to challenge our classical intuitions about locality and realism, pushing the boundaries of how we conceive the fabric of the cosmos. The first significant experimental tests of Bell's inequalities began in the 1970s and 1980s, with pioneering work by physicists such as Alain Aspect and his colleagues. Using carefully prepared pairs of entangled photons, these experiments measured correlations in the particle's properties, such as polarization, under varying conditions. Remarkably, the results consistently violated Bell's inequalities, demonstrating correlations stronger than any local hidden variable theory could account for. This meant that the entangled particles were connected in a way that defied classical notions of space and time, exhibiting what we now call quantum non-locality. The photons seem to know about each other's states instantaneously, regardless of the distance separating them, suggesting that entanglement was a genuine feature of the natural world rather than a mathematical artifact or experimental error. These experimental confirmations transformed entanglement from a theoretical curiosity into an established physical phenomenon, compelling physicists to rethink foundational assumptions about causality and information transfer in the universe. Subsequent experiments have refined and extended these initial findings, closing loopholes and enhancing the precision of measurements to rule out alternative explanations. Advances in technology have allowed entanglement to be tested over increasingly large distances, even between satellites and ground stations, reinforcing the conclusion that nature fundamentally exhibits non-local behavior. These groundbreaking experiments not only confirm the predictions of quantum mechanics, but also inspire new technological frontiers, such as quantum cryptography and quantum computing, which harness entanglement's peculiar properties for practical applications. Importantly, the experimental validation of Bell's theorem challenges our deepest intuitions about separateness and individuality, revealing a universe woven together by subtle threads that defy classical description. This recognition invites us to explore further the implications of non-locality, as well as the philosophical questions it raises about the nature of reality and information. As we reflect on these experimental triumphs, it becomes evident that Bell's theorem not only confirms the existence of entanglement, but also affirms that the quantum world operates beyond the constraints of classical locality. The particles' instantaneous correlations hint at an underlying order that transcends conventional space-time, suggesting that our universe may be interconnected in ways that challenge the very fabric of cause and effect. This realization opens new avenues for theoretical inquiry, encouraging physicists to seek unified descriptions that reconcile quantum mechanics with relativity and gravity. The strange, counterintuitive phenomena revealed by entanglement and non-locality thus serve as a gateway into a deeper understanding of the cosmos, beckoning us toward the next mysteries the quantum mechanics holds. It is from this vantage point that we proceed to examine further quantum phenomena, each adding intricate layers to our evolving picture of reality. Within the realm of quantum mechanics, particles exhibit behaviors that defy the straightforward expectations set by classical physics. One of the most intriguing of these behaviors is quantum tunneling, a phenomenon where particles can traverse energy barriers that, according to classical laws, should be insurmountable. Imagine a ball rolling toward a hill. If it lacks sufficient energy, classical intuition tells us it will simply roll back. Yet, at the quantum scale, particles do not behave like tiny balls, but rather like waves, whose probabilistic nature allows them to leak through barriers, appearing on the other side without ever having possessed the energy classically required to climb over. This passage through forbidden regions reveals the fundamentally non-intuitive nature of the quantum world, where certainty gives way to probability and possibility. The mathematical framework of quantum mechanics describes particles by a wave function, a complex entity that encodes the likelihood of finding a particle in a particular location. When this wave function encounters an energy barrier, it does not abruptly stop, but rather decays exponentially inside the forbidden region, retaining a small but finite amplitude on the other side. This residual amplitude corresponds to a measurable probability that the particle can emerge beyond the barrier, effectively tunneling through it. This counterintuitive process has been confirmed across numerous experiments, from electron tunneling in thin insulating layers to alpha decay in radioactive nuclei. Each observation reaffirms that the quantum world operates according to principles that transcend classical boundaries, inviting us to reconsider our concepts of motion, energy, and possibility. Quantum tunneling is not merely a theoretical curiosity. It underpins technologies that have become integral to modern life. One such application is the tunnel diode, a semiconductor device that exploits tunneling to achieve extremely fast switching speeds. Unlike conventional diodes, where current flows only above a certain threshold, tunnel diodes allow electrons to pass through potential barriers even at low voltages, enabling rapid response times and unique electrical characteristics. This innovation stems directly from the principles of quantum tunneling, demonstrating how abstract quantum phenomena can translate into practical devices. Moreover, tunneling is central to the operation of scanning tunneling microscopes, which allow us to visualize surfaces at the atomic level by measuring tunneling currents between a sharp tip and the specimen. These technologies illustrate how the strange behaviors of the quantum world enrich our capabilities, bridging the gap between fundamental physics and real-world applications. Beyond technological advances, quantum tunneling challenges our philosophical understanding of barriers and constraints. It compels us to accept that boundaries which seem absolute at macroscopic scales become permeable and probabilistic at the quantum level. This realization deepens our appreciation for the subtlety and complexity woven into the fabric of the universe. It also encourages ongoing exploration into phenomena such as tunneling time, coherence, and the interplay between quantum states and their environments. As we continue to investigate these mysteries, quantum tunneling stands as a testament to the unexpected and often paradoxical features that define the quantum domain. Having glimpsed the phenomenon of particles passing through seemingly insurmountable barriers, we are invited to explore yet another layer of quantum mystery. The journey leads us toward the realm of superposition and measurement, where the act of observation itself reshapes reality in subtle and profound ways. As we venture deeper into the quantum world, we encounter a principle that gently unsettles our classical intuitions: the Heisenberg uncertainty principle. At its heart lies a profound insight about the limits of what can be known simultaneously. Unlike the predictable motions of planets or the steady flight of a thrown ball, quantum particles evade such certainty. The principle states that there is a fundamental limit to how precisely one can know both the position and momentum of a particle at the same moment. This is not a limitation of our measuring instruments or experimental skill, but an intrinsic feature of nature itself. It implies that the more precisely we pin down where a particle is, the less precisely we can know how fast it is moving and in which direction. Conversely, trying to measure momentum with great accuracy blurs the particle's position. This dual uncertainty challenges the classical ideal of a clockwork universe, where all future states could, in theory, be predicted if initial conditions were fully known. Instead, quantum mechanics teaches us that at the smallest scales, reality resists such deterministic clarity. The origin of this uncertainty can be traced back to the wave-like nature of quantum particles. Unlike tiny billiard balls, particles such as electrons exhibit behaviors more akin to waves spreading across space. When we attempt to localize a particle to determine its exact position, we must use waves with many different momenta to create a sharp peak in space. However, this superposition of waves inherently leads to a spread in possible momenta. Conversely, a particle defined by a single momentum corresponds to a wave extending broadly in space, leaving its position undefined. This interplay between position and momentum is not merely a technical detail. It reveals a fundamental balance woven into the fabric of reality. Werner Heisenberg, who formulated this principle in 1927, showed that uncertainty is not a bug, but a feature of the quantum world. It is a reminder that, at its core, nature is probabilistic rather than deterministic, inviting us to embrace a more nuanced understanding of existence. The implications of the uncertainty principle ripple through many aspects of quantum theory and experimental practice. It sets a limit on the precision of measurements, guiding how physicists design experiments and interpret data. This principle also underlies the stability of atoms. Without such uncertainty, electrons might spiral inexorably into the nucleus, collapsing matter as we know it. Furthermore, it reframes the concept of causality and prediction in physics. While classical mechanics allows for precise forecasts given initial conditions, quantum mechanics introduces inherent unpredictability at fundamental levels. This unpredictability does not imply chaos, but a statistical framework where only probabilities can be assigned to outcomes. Thus, Heisenberg's insight reshapes our understanding of measurement and observation, revealing that the very act of probing quantum systems influences what can be known, blurring the boundaries between observer and observed. As we reflect on the uncertainty principle, we find ourselves at the crossroads where physics meets philosophy. It challenges the comforting notion that the universe is a clockwork mechanism waiting to be fully unveiled. Instead, it invites contemplation on the nature of knowledge itself, what it means to know, to measure, and to observe. The principle whispers of a universe more subtle and intertwined than our senses suggest, where certainty gives way to possibility, and where the act of looking alters the landscape observed. In this gentle surrender to uncertainty, quantum mechanics opens a door to deeper mysteries, preparing us to explore phenomena even more bewildering, such as entanglement and non-locality. When we look around at the world, everything appears solid, definite, and predictable. Yet, at the smallest scales, quantum mechanics reveals a reality that is anything but certain. Particles exist in delicate superpositions, simultaneously occupying multiple states until observed. This strangeness, however, seems absent from our everyday experiences. This apparent disconnect between the quantum and classical worlds has puzzled scientists for decades. The key to understanding this lies in a subtle process known as quantum decoherence. Decoherence occurs when quantum systems interact with their surroundings. The environment made up of countless particles, photons, and fields. These interactions cause the fragile quantum states to lose their coherence, effectively spreading out the quantum information into the environment. This process transforms the weird, overlapping possibilities of quantum states into the definite outcomes we observe, bridging the gap between the microscopic and macroscopic realms. It explains why objects around us don't appear to be in multiple states at once, despite the underlying quantum nature of matter. To envision decoherence, imagine a perfectly still pond where ripples represent quantum states. When left undisturbed, these ripples can overlap, creating intricate patterns of interference. Yet, toss a handful of pebbles into the water, and the delicate patterns quickly dissolve into a chaotic, unrecognizable surface. In a similar way, any interaction between a quantum particle and its environment acts like those pebbles, scattering the quantum information and destroying the delicate superposition. The environment acts as a constant observer, recording and dispersing information about the quantum system. This continuous interaction effectively measures the system, but in a passive and unavoidable manner, causing the quantum states to appear classical. It is not the act of human observation alone, but the pervasive influence of the environment that suppresses quantum weirdness in the world we perceive. Through decoherence, nature itself performs countless measurements, ensuring that the strange quantum phenomena remain hidden from our everyday senses. Decoherence also provides insight into the enduring puzzle of the quantum measurement problem. Why the act of measurement collapses a quantum state into a definite outcome. Rather than invoking mysterious observers or consciousness, decoherence reveals that the environment's role is fundamental. As quantum states become entangled with the environment, the superposition effectively branches into distinct, non-interfering alternatives, each corresponding to a classical reality. This branching explains why we perceive a single outcome, even though all possibilities may persist in a vast quantum landscape. Yet, this process unfolds without any magical collapse. It is a natural consequence of quantum systems interacting with the complex environment that surrounds them. This perspective helps to reconcile the microscopic quantum world with the macroscopic classical world, showing that the strange quantum effects recede naturally into the background noise of the universe. The implications of decoherence stretch beyond pure theory, influencing emerging technologies such as quantum computing and quantum cryptography. In these fields, preserving coherence, maintaining delicate quantum states despite environmental interactions, is a significant challenge. Understanding how decoherence operates allows scientists to devise methods to shield quantum systems, prolonging their quantum behavior to harness their power for computation and secure communication. Yet, it also reminds us that the quantum classical boundary is not sharply defined, but a gradual transition shaped by the environment's omnipresent influence. This continuous interplay between quantum possibilities and classical realities invites us to reconsider our place in the cosmos as part of a universe where certainty and uncertainty coexist in a delicate balance. As we move forward, this balance will guide our exploration of deeper quantum mysteries, including the enigmatic phenomena of entanglement and non-locality. At the heart of quantum computing lies the remarkable phenomenon of superposition, where quantum particles exist in multiple states simultaneously, defying the classical notion of a single, definite condition. Unlike classical bits, which are either 0 or 1, quantum bits, or qubits, can embody both states at once, enabling a vast computational space to be explored in parallel. This intrinsic property allows quantum computers to process complex problems more efficiently than traditional machines. Yet, the concept challenges our everyday intuition, as it seems to suggest that a particle could be in many places or states simultaneously until observed. This strange behavior is not merely theoretical. It forms the foundation of quantum algorithms that promise breakthroughs in fields ranging from cryptography to materials science. As we learn to control and maintain these superpositions, despite their fragile nature, we unlock new dimensions of computational power previously thought impossible. The ability to harness such quantum states requires exquisite precision and environmental isolation, emphasizing the delicate dance between coherence and decoherence that governs quantum systems. Complementing superposition is the phenomenon of entanglement, a deeply counterintuitive connection between particles that Einstein once described as spooky action at a distance. When particles become entangled, their states become intertwined, such that the measurement of one instantly influences the state of the other, regardless of the distance separating them. This non-local correlation defies classical explanations and has profound implications for information processing. In quantum computing, entanglement serves as a vital resource, enabling qubits to work in concert in ways that exponentially expand computational capabilities. By creating networks of entangled qubits, quantum computers can perform operations that leverage these instantaneous correlations, dramatically improving efficiency and opening doors to solving problems deemed intractable for classical computers. The challenge lies in generating and preserving entanglement in a controlled environment, as any interaction with the outside world risks collapsing these fragile states. This interplay between entanglement and decoherence is central to advancing quantum technologies and reveals the subtle and surprising fabric of reality itself. Building upon superposition and entanglement, quantum computing harnesses these phenomena to explore computational landscapes in unique ways. Unlike classical logic gates that process bits sequentially, Quantum gates manipulate qubits through unitary transformations, preserving coherence and enabling complex interference patterns. These operations allow quantum algorithms to traverse solution spaces more efficiently, finding answers by amplifying correct outcomes and cancelling out incorrect ones. This approach holds promise for optimizing logistics, simulating molecular interactions with unprecedented accuracy, and breaking encryption schemes that safeguard modern communication. However, the path to practical quantum computing is fraught with technical and conceptual challenges. Maintaining qubit coherence over extended periods, implementing error correction in a quantum framework, and scaling systems to millions of qubits are active areas of research. Each step forward brings us closer to realizing quantum machines capable of transforming science, technology, and society. The strange, counterintuitive principles of quantum mechanics are no longer confined to abstract thought experiments, but are becoming tangible tools that redefine computation itself. As quantum computing continues to evolve, it also reshapes our understanding of information and reality. By exploiting entanglement and superposition, these machines embody a new mode of processing that transcends classical limitations, inviting us to rethink the nature of knowledge and certainty. The quantum realm teaches us that information is not merely stored or transmitted in fixed states, but flows dynamically through probabilities and correlations that resist classical description. This perspective has profound implications beyond computation, influencing secure communication protocols like quantum cryptography, which leverages these principles to guarantee unbreakable security. The convergence of theory and technology in quantum computing exemplifies how embracing the strangeness of quantum mechanics can yield powerful and practical innovations. As researchers continue to unravel these mysteries, the horizon of what we can compute and understand expands, guided by the delicate interplay of coherence, entanglement, and measurement. In this unfolding landscape, we glimpse a future where the quantum fabric of reality becomes a canvas for human ingenuity and discovery. At the heart of quantum cryptography lies a remarkable principle: the ability to detect any eavesdropping attempt through the fundamental laws of physics themselves. Unlike classical encryption methods that rely on complex mathematical problems for security, quantum cryptography draws its strength from the peculiarities of quantum mechanics. Central to this approach is the phenomenon of quantum entanglement, where two particles become so deeply connected that the state of one instantly influences the state of the other, regardless of the distance separating them. This intrinsic link allows for the creation of shared, secret keys between communicating parties with an unprecedented level of security. Any attempt to intercept or measure these quantum states inevitably disturbs them, revealing the presence of an intruder. This is because quantum information cannot be copied or observed without altering its delicate state, a feature known as the no-cloning theorem. Thus, the very act of spying betrays itself, ensuring that the communication remains secure, or the breach is immediately known. The elegance of quantum cryptography lies in its marriage of theory and experiment, where abstract quantum rules translate into practical safeguards for information exchange, offering a glimpse into a future where privacy is grounded not in computational difficulty, but in the immutable fabric of reality itself. The most widely studied protocol in quantum cryptography is quantum key distribution, or QKD, which relies on encoding information in the quantum states of photons, particles of light. These photons can be prepared in superpositions of polarization states, enabling them to carry information in ways that defy classical intuition. When two parties, often called Alice and Bob, exchange these quantum bits, or qubits, their measurements yield correlated outcomes that form the basis of a shared secret key. The beauty of QKD is that it harnesses the probabilistic nature of quantum measurement. Any disturbance caused by an eavesdropper, Eve, changes the expected correlations, thereby alerting Alice and Bob to the intrusion. The process involves comparing subsets of their data over a public channel to estimate the error rate, and if it remains below a certain threshold, they can be confident that their key is secure. Advances in experimental techniques have brought these protocols from theoretical constructs to real-world applications, with fiber optic networks and satellite links demonstrating secure quantum communication over impressive distances. This progress reflects a profound shift from reliance on mathematical complexity to the utilization of physical laws themselves as guardians of secrecy, marking a new chapter in the story of secure communication. Entanglement-based quantum cryptography further deepens this narrative by exploiting the shared quantum states between distant particles. In this approach, entangled pairs are distributed to communicating parties, whose measurements yield correlated results that form the secret key. The remarkable aspect here is that security does not depend on trusting the devices or channels involved, but rather on the very presence of quantum correlations that cannot be mimicked by classical means. This device-independent security is a profound consequence of Bell's theorem and quantum non-locality, which demonstrate that entangled particles behave in ways incompatible with any local hidden variable theory. By testing for violations of Bell inequalities during the key distribution process, users can certify the authenticity of their quantum connection, even in the presence of potentially compromised equipment. This feature elevates quantum cryptography beyond traditional paradigms, offering a robust shield against increasingly sophisticated attacks. As technology advances, implementing such entanglement-based protocols in networks becomes a tantalizing prospect, promising communication channels whose security is assured by the deepest principles of quantum physics. The interplay of entanglement, measurement, and trust forms a delicate tapestry upon which the future of secure information exchange is being woven. The practical realization of quantum cryptography, however, faces challenges rooted in the fragility of quantum states and the need for precise control over quantum devices. Maintaining coherence and minimizing noise over long distances require sophisticated engineering and innovative error correction methods. Despite these hurdles, experimental achievements continue to push boundaries, with quantum networks now spanning cities and even connecting continents via satellites. These milestones hint at a future where secure communication is not a luxury, but a fundamental right, safeguarded by nature's own rules. Moreover, The integration of quantum cryptographic techniques with classical infrastructure offers a pathway toward hybrid systems that leverage the best of both worlds. This gradual fusion of quantum and classical technologies underscores a broader theme in quantum information science: the harmonious coexistence of new principles with established frameworks, enabling transformative applications while respecting practical realities. As researchers refine these technologies and expand their reach, the promise of truly unbreakable codes moves ever closer to becoming an everyday reality. Quantum mechanics, with its enigmatic principles and counterintuitive phenomena, has long been considered the domain of the microscopic world: particles, atoms, and subatomic interactions. Yet, recent scientific inquiries invite us to ponder a profound question. Could the strange laws of quantum physics extend their subtle influence into the realm of living organisms? This emerging field, known as quantum biology, explores how quantum effects might underpin certain biological processes that classical physics alone struggles to explain. Among the most captivating examples are photosynthesis in plants and the navigation abilities of migratory birds, where quantum coherence and entanglement could play vital roles. These investigations challenge our traditional understanding of life and hint at a deeper, more interconnected relationship between biology and the fundamental workings of the universe. As we delve into these phenomena, it becomes clear that life itself may be more intimately linked to quantum mechanics than previously imagined. Consider photosynthesis, the process by which plants convert sunlight into chemical energy, a marvel of efficiency that has fascinated scientists for decades. Classical explanations, while informative, have struggled to fully account for the remarkable speed and precision with which energy is transferred within photosynthetic complexes. Intriguingly, experiments suggest that quantum coherence, where particles exist in multiple states simultaneously, might facilitate this energy transport. In essence, excitons, the energy carriers generated by absorbed photons, appear to explore multiple pathways concurrently, selecting the most efficient route to reaction centers. This quantum walk enables near-perfect energy transfer, minimizing losses and enhancing the plant's ability to harness sunlight. Such findings not only deepen our understanding of photosynthesis, but also inspire the design of advanced solar energy technologies that mimic nature's quantum strategies. The implications of quantum coherence in biology extend far beyond photosynthesis, inviting a reconsideration of how quantum phenomena might influence life's fundamental processes. Another striking example of quantum biology emerges in the mysterious navigational prowess of migratory birds. Species such as the European robin traverse thousands of kilometers with astonishing accuracy, guided in part by Earth's magnetic field. The underlying mechanism, often referred to as the radical pair hypothesis, proposes that quantum entanglement, where particles become linked such that the state of one instantly influences the other, plays a crucial role. Within specialized proteins called cryptochromes, Light-induced radical pairs may form entangled states sensitive to magnetic fields, effectively acting as a biological compass. This quantum sensitivity allows birds to perceive geomagnetic information in ways that classical physics cannot easily explain. Such discoveries hint at a sophisticated natural exploitation of quantum mechanics, woven seamlessly into the fabric of life's navigation systems. Exploring these quantum effects in living organisms opens new frontiers, bridging physics, chemistry, and biology in unexpected harmony. The exploration of quantum biology prompts us to reconsider the boundaries between the quantum and classical worlds. Traditionally, the fragile nature of quantum states suggested that biological systems, with their warm and noisy environments, would be inhospitable to delicate quantum phenomena. However, mounting evidence reveals that life may have evolved mechanisms to preserve and harness these quantum effects, even amid apparent chaos. The interplay between coherence, entanglement, and biological function challenges conventional wisdom and invites interdisciplinary collaboration to unravel these complex interactions. Such insights not only enrich our appreciation of nature's ingenuity, but also pave the way for novel technologies inspired by life's quantum secrets. As research progresses, the subtle quantum threads woven through the tapestry of life continue to emerge, offering a glimpse into a world where biology and quantum physics unite in profound ways. As we delve deeper into the mysteries of quantum mechanics, we encounter interpretations that challenge our most fundamental understanding of reality itself. Among these, the many worlds interpretation stands as one of the most mind-bending and thought-provoking. First proposed by physicist Hugh Everett III in the 1950s, this interpretation suggests that every quantum event, every time a particle chooses a path or a state, does not simply resolve into a single outcome. Instead, the universe splits, branching into multiple parallel universes. Each of these universes embodies a different possible outcome, existing simultaneously but separately from one another. This idea turns our classical intuition on its head, proposing a vast, possibly infinite multiverse where every conceivable history and future plays out in its own realm. The seemingly random and probabilistic nature of quantum events, rather than collapsing into one reality, actually spawns a complex web of realities, expanding the very fabric of existence. The implications of the many worlds interpretation ripple through the foundations of physics and philosophy alike. It dispenses with the need for wave-function collapse, a concept in traditional quantum mechanics where a quantum system abruptly settles into a definite state upon measurement. Instead, the wave function continues its deterministic evolution, branching endlessly. This removes the ambiguity and observer dependence that have long puzzled scientists and thinkers. Although the idea may seem fantastical, it offers a coherent mathematical framework consistent with the Schrödinger equation and quantum formalism. Yet, the notion of countless coexisting universes raises profound questions about identity, causality, and free will. If every possible outcome unfolds somewhere, What does this mean for our understanding of choice and consequence? While these questions venture into metaphysics, they highlight how quantum theory challenges not only physics, but our worldview itself. From a scientific perspective, the many worlds interpretation invites us to reconsider the nature of measurement and observation. In this picture, the act of observing is just another quantum event that causes the universe to branch into multiple versions. Each observer experiences a distinct reality corresponding to the outcome they perceive. This elegantly sidesteps the so-called measurement problem, where the mechanics of wave function collapse remain mysterious. Though direct experimental evidence for these parallel universes remains elusive, the interpretation maintains internal consistency and aligns with known quantum behavior. It also inspires new avenues of thought in quantum computing and information theory, where superposition and entanglement harness the multiplicity of potential states. The many worlds interpretation thus not only reshapes our understanding of quantum phenomena, but also offers a fertile conceptual landscape for future explorations. Despite its elegance, the many worlds interpretation is not without its critics and controversies. Some argue that it introduces an extravagant ontology, an infinite proliferation of unseen universes that, while mathematically permissible, may be metaphysically excessive. Others seek experimental tests or alternative interpretations that preserve a single, objective reality. Nonetheless, the notion of a multiverse born from quantum events continues to captivate scientists, philosophers, and the public imagination alike. It serves as a reminder that at the quantum level, reality is far stranger and more intricate than everyday experience suggests. This conceptual leap encourages us to embrace uncertainty and complexity as fundamental features of the cosmos, rather than obstacles to understanding. As we reflect on the many worlds interpretation and its profound implications, we find ourselves at the threshold of a reality that transcends classical boundaries. Whether these parallel universes remain an elegant theoretical construct or reveal deeper truths about existence, their possibility enriches the narrative of quantum mechanics. This expanding vision invites us to explore not only the microscopic phenomena that govern particles, but also the vast, interconnected structure of reality itself. From the quantum mysteries woven into biological systems to the cosmic scale of universes yet unseen, the journey of discovery continues, leading us toward ever more wondrous horizons. At the heart of quantum mechanics lies a tapestry of phenomena that quietly defy our everyday intuitions about reality. Unlike classical physics, which presents a world of definite positions and predictable trajectories, quantum systems exist in superpositions, states that are not simply one thing or another, but a blend of possibilities until measured. This fundamental uncertainty challenges the very notion of a fixed reality, suggesting instead that what we observe may depend on the act of observation itself. Such an idea unsettles our traditional views of an objective world, implying that the fabric of reality might be more fluid and interconnected than previously imagined. This subtle interplay between measurement and existence invites us to reconsider the role of the observer and questions whether reality is something independent or co-created through interaction. Beyond the elusive nature of superposition, quantum mechanics introduces us to phenomena that further stretch our understanding of causality. Entanglement, for instance, reveals that particles can become linked in ways that transcend spatial separation, such that the state of one instantly influences the state of another, regardless of distance. This spooky action at a distance, as Einstein famously described it, appears to defy the classical principle that no influence can travel faster than light. The implications of entanglement ripple through our concepts of cause and effect, challenging the idea that events unfold in a simple, linear sequence. Instead, quantum theory suggests a more holistic perspective, where interconnectedness and non-locality might play fundamental roles in the structure of the universe. The philosophical ripples of quantum mechanics extend further into the realm of determinism, a cornerstone of classical physics that posits a predictable universe governed by cause and effect. In the quantum domain, however, indeterminacy reigns supreme, as the outcome of certain measurements can only be described probabilistically. This intrinsic randomness forces us to confront the possibility that the universe is not fully predetermined, but contains elements of genuine unpredictability. Such a departure from strict determinism has profound consequences for how we understand free will, the flow of time, and the very nature of existence. It invites a reconsideration of whether the future is set in stone or open to multiple possibilities, a question that resonates deeply within both science and philosophy. As we navigate these complex landscapes, interpretations of quantum mechanics offer diverse lenses through which to view reality. From the Copenhagen interpretation's emphasis on wave function collapse to the many worlds hypothesis proposing branching universes, each framework grapples with the tension between observation and existence in its own way. These perspectives underscore the richness of quantum theory, not merely as a tool for predicting experimental outcomes, but as a profound inquiry into the nature of reality itself. Such philosophical explorations encourage a humble acknowledgement of the limits of human understanding and a recognition that the universe may be more mysterious and wondrous than our classical intuitions allow. In recent years, the field of quantum mechanics has witnessed a remarkable surge in experimental breakthroughs that continue to challenge and expand our understanding of the microscopic world. Among these, quantum teleportation stands as a beacon of progress, demonstrating the extraordinary ability to transmit the quantum state of a particle instantaneously across distances without moving the particle itself. This phenomenon, rooted in the enigmatic property of entanglement, allows two particles to share a connection so profound that the state of one instantly reflects the state of the other, regardless of the space that separates them. These experiments are not mere curiosities. They pave the way for revolutionary technologies like ultra-secure quantum communication networks and quantum computing architectures. By pushing the limits of how information can be transferred and processed, quantum teleportation embodies the ongoing dialogue between theory and practice, where abstract mathematical principles manifest in tangible, awe-inspiring results. As scientists refine their techniques and explore new materials and configurations, the boundaries of what is possible continue to expand, inviting us to reconsider the very fabric of reality itself. Another captivating development in this realm is the discovery and study of time crystals, exotic phases of matter that defy conventional expectations about temporal symmetry. Unlike ordinary crystals, which exhibit repeating patterns in space, time crystals display a structure that repeats in time, oscillating between states without the input of energy. This perpetual motion within a quantum system challenges the classical understanding of thermodynamics and stability, offering a glimpse into new states of matter that were once thought impossible. Time crystals have been realized in laboratory settings using trapped ions and superconducting qubits, where precise control over interactions and coherence times allows these unique oscillations to persist. The implications of such discoveries ripple through the foundations of physics, suggesting that the interplay between time and quantum states holds secrets that may unlock novel approaches to quantum computation and information storage. As researchers continue to delve deeper, each experiment reveals layers of complexity and nuance, underscoring the subtle harmony between order and disorder that quantum mechanics orchestrates. Alongside these remarkable feats, advances in manipulating quantum systems have enabled experiments that probe the very boundaries of causality and measurement. Quantum systems have been subjected to increasingly delicate observations, where the act of measurement itself can alter outcomes in ways that defy classical logic. For instance, weak measurements allow glimpses into quantum states without fully collapsing their wave functions, providing insights into the probabilistic nature of quantum events. Meanwhile, experiments testing entanglement across larger distances and with more complex particles continue to solidify the non-local character of quantum correlations. These studies not only affirm the theory's predictions, but also challenge us to rethink the classical assumptions about space, time, and information. The ongoing refinement of experimental techniques, from ultra-cold atoms to photonic networks, fosters an environment of relentless curiosity and discovery, where each new result deepens the mystery and beauty of the quantum world. In this unfolding narrative, the boundary between the known and the unknown remains fluid, inviting endless exploration and wonder. As we look toward the horizon of quantum mechanics, the future holds a landscape rich with both promise and profound questions. The development of quantum technologies, such as quantum computing, quantum cryptography, and quantum sensing, hints at transformative changes in how we process information and secure communication. Yet, behind these advancements lie puzzles that remain deeply unresolved. The measurement problem, for example, continues to challenge our understanding of what truly occurs when a quantum system interacts with its environment. Does the wave function collapse in a physical sense, or is this a reflection of our limited perspective? Furthermore, The quest to unify quantum mechanics with general relativity remains an elusive goal, urging physicists to seek a coherent theory of quantum gravity. Such a theory would illuminate the behavior of the cosmos at the smallest scales and the most extreme conditions, potentially revealing new layers of reality beyond our current comprehension. This interplay between technological innovation and foundational mystery fuels a dynamic tension, where each breakthrough opens new doors while uncovering deeper enigmas. Another compelling avenue lies in exploring the nature of quantum entanglement and non-locality on ever grander scales. Experiments pushing entanglement beyond microscopic particles toward larger, more complex systems challenge our classical intuitions about separability and locality. Could entanglement play a role in biological processes, or even consciousness, as some speculative theories propose? While such ideas remain controversial, they underscore the openness of quantum mechanics to unexpected domains. Additionally, the emergence of quantum simulations allows scientists to model complex quantum systems that are otherwise intractable, offering glimpses into exotic phases of matter and chemical reactions. These simulations may help decode phenomena ranging from high-temperature superconductivity to the behavior of materials under extreme pressures. In this way, quantum mechanics serves as both a tool and a frontier, expanding our capacity to understand and manipulate the physical world in ways once considered impossible. The horizon is broad, filled with potential discoveries that could reshape science and technology alike. Yet, as we gaze into this expanding quantum realm, we must also acknowledge the philosophical and conceptual challenges that persist. Interpretations of quantum mechanics, from the many worlds hypothesis to pilot wave theories, offer diverse perspectives, but no definitive consensus. These interpretations influence how we conceive of reality itself, whether the universe branches into countless parallel worlds, or whether hidden variables underlie the apparent randomness. Moreover, questions about the flow of time, causality, and the role of the observer remain open, inviting us to reconsider the very foundations of physics. The experimental tools at our disposal continue to sharpen, but the ultimate meaning of the quantum formalism may forever elude a simple explanation. This ambiguity is not a failure, but rather an invitation to embrace uncertainty and to cultivate a deeper philosophical dialogue alongside empirical inquiry. In this way, quantum mechanics transcends the boundaries of science, touching upon the mysteries that have fascinated humanity for centuries. As we reflect on the peculiar and often bewildering features of quantum mechanics, it becomes clear that this field does more than challenge our scientific understanding. It expands the very horizons of human imagination. The phenomena of superposition, entanglement, and wave-particle duality defy classical logic, yet reveal a universe of profound subtlety and interconnectedness. Each experiment that probes these quantum mysteries invites us to question deeply held assumptions about nature, encouraging a mindset that is open to wonder and complexity. This openness nurtures not only scientific progress, but also a richer appreciation of the world around us, where certainty gives way to possibility, and where the boundaries between observer and observed blur into intriguing new relationships. In embracing this quantum strangeness, we allow ourselves to see beyond the familiar, stepping into a realm where the unexpected becomes a source of inspiration rather than unease. The journey through quantum mechanics also highlights the collaborative spirit of human inquiry. Scientists, philosophers, and thinkers from diverse disciplines contribute to a shared quest to unravel the quantum enigma. This collective pursuit reflects a profound curiosity that transcends cultural and temporal boundaries, reminding us that exploration is a fundamental human trait. Each new insight, no matter how subtle, builds upon the work of countless minds, weaving a tapestry of knowledge that continues to grow in depth and nuance. The ongoing dialogue between theory and experiment, between prediction and observation, exemplifies a dynamic process that keeps science vibrant and alive. In this light, quantum mechanics is not a closed book, but an open invitation, a doorway to questions that inspire future generations to push the limits of understanding even further. Beyond its scientific implications, quantum mechanics encourages a gentle humility in the face of nature's mysteries. It teaches us that some aspects of reality may forever elude complete explanation, reminding us that uncertainty is not a weakness, but a fundamental feature of the cosmos. This recognition invites a different kind of knowledge, one that embraces ambiguity and values the search itself as a meaningful endeavor. By accepting that certain answers may remain out of reach, we cultivate patience and awe, qualities that enrich our experience of the universe. Such a perspective fosters a respectful relationship with the unknown, where science and philosophy coexist in a harmonious dance. In this way, quantum mechanics becomes a source of quiet inspiration, encouraging us to remain curious and open-hearted as we continue to explore the depths of existence. Ultimately, the strange, counterintuitive nature of quantum mechanics challenges us to rethink what it means to understand the world. It invites us to expand our conceptual frameworks and to embrace complexity without fear. This expansion of thought is a testament to the resilience and creativity of the human mind, capable of reaching beyond the visible and tangible to grasp the subtle fabric of reality. As we continue to develop new technologies and theories inspired by quantum phenomena, we also nurture a spirit of exploration that enriches both science and culture. Through this ongoing journey, quantum mechanics stands as a beautiful reminder that the universe is far more wondrous and mysterious than we might have ever imagined. In closing, the strange world of quantum mechanics invites us to celebrate curiosity itself, the driving force behind discovery and innovation. By embracing the unknown and welcoming the surprises it holds, we open ourselves to new ways of thinking and being. This openness not only advances our scientific frontiers, but also deepens our connection to the cosmos and to one another. As we continue to explore the quantum realm, may we carry forward a sense of wonder and humility, recognizing that each question answered births new mysteries to explore. In this endless dance between certainty and uncertainty, the human spirit finds its greatest expression. Thus, quantum mechanics is not just a field of study, but a profound journey into the heart of reality, inviting us all to dream, to learn, and to imagine what lies beyond.